So I'm very pleased this week to introduce Charles Haynes. So I should give you a little bit of background about Charles. So he claims since he's no longer young, he's done a lot of things in his life, but I think it's just in fact that he's done a lot of things in his life. So he originally trained as an architect. He was involved with building houses at UBC and designing houses, Habitat House in Vancouver. He was involved with video displays, with interactive displays for the military. With he designed credit card, internet card processing devices. He got involved with radar, building other houses in Vancouver, for which he won various heritage awards. And then since about 2010, he's been heavily engaged in wave energy projects. So he describes himself as an inventor and entrepreneur. And anybody who's walked around the headlands at UBC will have seen off Point Grey, there's this sort of yellow mushroom kind of thing in the water, and you wonder what it is. And that's what Charles is going to tell us about today. So it's all yours, Charles.
Well, thank you very much, Douglas. So what happened was my wife said, we need to have the solar energy on our cabin at Keats Island. And of course, I know it rains here. And then I woke her up one morning at 3 a.m. and we went out on the deck and I said, look at that. Isn't that amazing? And she said, yeah, what am I looking at? And I said, the waves, they're running all night. And so then I kind of thought, I'll just buy a wave machine. And instead of having, solar that doesn't work at night and wind. And then I tried to buy these machines. This was in 2010, and there are none. And even to today, there are none. And this thing got bigger and bigger and bigger. And now it's 100 tons. And I've spent $5 million on it. And I got it working now. It's quite exciting, actually. So that's the short part of that. And I'm just going to talk over this slide. But the main thing is we're going to have little 2-minute breaks so I can hear from you and you can ask the question that you really want to know that I hope I can help you with. The thing that I've done is I noticed that a half-meter wave that runs 2 seconds, the period's 2 seconds, then you'd have 30 waves in a minute, and you'd have an up and down distance of 1 meter, so that's 30 meters. If you had a 1 meter wave and it was 5 seconds, which is perfectly reasonable, you get 12 per minute, up and down 2 meters, so you've got 24 meters. So the littler wave is 20% bigger in terms of its distance. And I thought that was quite important, since everybody else was talking about the giant waves, which are really horrible to be involved with. They'll break almost anything. So just being a chicken, I went, well, let's just use the little waves. And that was one of my first rules, work with small waves. Second rule was to work near shore where the transmission lines can go through the air, just like they normally do. And to put the generator on top of the machine out of the water. So those are my 3 rules. And in a little while, we're going to run through the 10 years of this and you'll see perhaps how those fit. Now, wrong button. Now, we're going to have a little video. This video is going to run twice and it takes, I think, 11 seconds. And all you're going to see is the major float move up and down. That float is 3 meters in diameter and 2 meters thick. And so there you go. Riley's going to run.
Here we go.
You can look at the wave. Oh, we just let it run.
One more time.
Here. A little bit jerky. Okay, so the main thing that I was hoping you would see was that the waves were not very large, but that float was moving in sync with the waves. And for your information, that weighs 10 metric tons, that float. Now I'm going to give you the introduction. So looking when you deal with small waves, as you can see at the bottom of the screen, where my focus is the 2-meter wave. And if you look on the screen again, you can see all of the blue area, which actually makes it suitable for 150 countries. That 75% of all the countries in the world are suitable for wave energy, in my opinion. Here's some little bit examples of that. The Orkney test site in Scotland is sort of the gold standard. And you can see that the waves there are not all that large on the average. They don't tell you what their average of the 90% of their waves is, but they do give their maximum one of 19 meters, which from my point of view is very, very scary. We look at Ucluelet and we've got 2.2 meters. It's almost the same in terms of average. Very nice. 90% of the waves are under 2 meters, and the biggest wave is 8 meters. Still a very big wave. And the English Channel, I've done a study on that, and there it's a little bit smaller, and so that's some information on that. Whoops, sorry. How do we go? In terms of wave energy and environmental concerns, basically there's none. It helps the situation. There's been studies on environmental noise, and of course it depends upon the machine. Here is the very nice chart of some comparisons. The main thing I was trying to compare here is the plant area to produce 1 terawatt hour. So in terms of kilometers squared. And if you look at the fossil fuel group, natural gas, oil, nuclear, etc., you see that the biggest one there is hydro dams, which we know take up a huge area. And they're 11 square miles, or square meters, or whatever it is, kilometers. And when we look at the renewables, we find that wind, it's unbelievably huge because of the spacing they have to have. Solar is around the same size as hydro, and wave is in the same range as the fossil fuel plants. And that's because of the energy density that's available in the water. Here's another picture you haven't seen before because I just made it. I'm trying to articulate, the yellow background is 100% energy for 24 hours, and the colored areas show you what you get in the different systems. The key part about wave energy is that it's continuous variable. The others are intermittent variable. They actually stop. This is where the test station is. And one of the key things that I have is the government buoy, and it's 35 kilometers away. And I've got official data from that buoy. I'm now okay, we're going to stop. I'll go back to that. That's the end of the introduction. I've on the right-hand side, you can see the contract with the BC government for, it's called an investigative use license. It's 5 years, it's renewable, and it allows me to investigate the use of something. In this case, it's wave energy, and that's the contract. That took about a year to get, and you have to submit things to basically everybody that has any kind of interest in the water, harbors, Transport Canada, fisheries, hydrographics, all of those guys. Okay, so now I'm just giving you a little background. I know that this business that I'm in is applied science, and I know that generally you're a little more pure science. But that is the world of wave energy right there. I'm going to go through each one really fast. The first one is the point absorber, which essentially is a float that moves up and down with the waves, and it's restrained in some way. The one at the top is a floating point absorber. These don't work. Number 2 and number 4 do not work. They fall over. Number 3 is a nice idea. It's a point absorber. It's got a base. It sits on the floor, on the seafloor, and it's the point absorber is the yellow thing at the top. It's a float. And what this does is it pulls a linear generator up and down inside that tank. This also doesn't work. The next one, which was one of my big favorites, is a Denmark project, Wavestar. They were not able to produce any power with that. The reason it's on that big, huge 4 posts with those holes is the idea was that when the storm came, they could jack it up out of the water. That's also, my approach is you make it strong enough that it can handle storm. Here's the famous Palamas. They went bankrupt in, I think, 2014. I can't actually read that part of the slide. This is a very cool idea, this attenuator. It means when one part of the wave is going up and the other part is going down, you use those 2 movements against each other so that you've got something to work to move the generator with. What I'm doing is putting a pile in and moving against that thing solid on the bottom. Number 3 is a brand new one. So far, none of these have worked. Well, they work and they produce power, but it's not economical. It's the main thing. These are also directional. They usually are stuck, and there's all sorts of issues with them. Here's a system that has never been built. All the pictures here are artist renderings. It's a good idea. Basically, it says that when the wave goes over top, there's a bunch of water that wasn't there a few seconds ago, and the weight of that water could be used to push something down, and then you would use that. Never built. Here's one. The patent was from 1902, the first really good patent on it. You can see that in number 1. Number 2, Aquamarine, nice little machine they built. Here they spent in excess of 50 million pounds on it, and didn't work. Somebody else is still working on this, Wave Roller. They claim that theirs works, and yet they never give any data. Here's one that does work, and the idea comes from this patent, 1910 patent, where you can see this allows for the tide, and the water will come in. And so what happens is the water comes rushing in and essentially compresses the air. Then the air blows up a pipe and turns a fan on the top, turbine. And been lots of disasters with these. 2 and 3 sank. Number 4 has just been built, put in Hawaii. No data. They've already had, they've had a couple of these, but they never tell us what it is. Number 5 does exist, and you can see that it produces what sort of power it produces, what it cost, and its best feature is that it's an effective breakwater. This is another method, which is the weirdest thing, because if you look in the picture number 1, the wave slides up the slope, goes into the pool, and then it drains down. And when I went to school, they told me you need to have a head. It's all about the head on generating water, with dams and rivers and all that. And the head here is like 1 meter. And in fact, I don't even know why the water comes out when I make a pool. And anyways, so they've done this for many years, and there's a little bit of data, and I'd like you to look at table 1. I wish we could spend some time on this, but this is a very weird numbers. I mean, how do they get 7 megawatts, 7,000 kilowatts at the bottom, and then when the time period gets longer, it goes down. Well, that's actually right, but it isn't right. This whole picture is not. We'll get into that in a few minutes. The blue line at the bottom is the best information we've got about power output from them, and this is from 2004. We're coming now near to the end of these. This is the Wello main one. Both of these are put out by oil companies that are moving into the renewables. And the idea is that the thing rocks, and there's a ball or something that rolls around inside, and that is used to generate the electricity. They keep making these, but we never get any data. How do I get this to go? And now, so since they don't work very well, people are trying to combine other things, and there's a big push on to get floating offshore wind turbines, because you can put them outside and there's, further away. And then they're trying to combine things with them. And so these are brand new devices, although the floating PowerPoint people haven't done anything since 2 years ago. It's a little bit sad, actually, all this. Okay, that's the end of that section. And this is what I've been doing. I've got 5 prototypes in the water. I've spent $5 million, and I've survived 2 hurricane-rated storms. We don't really get that much, but there's been in excess of 100-kilometer winds out there. I think the reason that I've been able to go through this and others haven't is I'm not depending upon grant money or writing grant proposals or being concerned about spending the money according to qualifying expenditures or writing reports about what I've done. I just do it, don't like it, change it, and keep going. And I think the main feature I've got, which I get from architecture, is I have no preconceived ideas of what this thing should be. I'm just trying to get it to work. And I started with the linear generator, which you saw other people have proved doesn't work, which is a float up that somehow moves magnets past some wires and generates electricity. The problem with that is it goes too slow. So I tried to make it faster, and I made a compound lever system. And then I only made one of these and looked at it and went, well, gee whiz, I've reinvented the round rotational generator. And so that's how I can get some higher speed out of it. So then I made a generator and figured out a system in 2013, which I patented, which is a very simple device to take reciprocating, oscillating motion and convert it into one-way rotation motion. Oh, pardon me. I've just jumped ahead here. There we are. So there's a bigger picture of that thing in 2013. What that does is it turns up and down motion into a power stroke that turns the generator on each one. This is a wave tank I made in a building I have in Vancouver, and we put it in a 40-foot container and had a bunch of people make waves. Too bad we don't have a wave pool here. We used to have a wave tank. It's gone. It would be sure nice. Now, then 2015, I made the complete system. The motive float, as we call it, is the in the center between the black balls. What I was trying to do was use plastic, aluminum, and wood, known products that I thought would work well at the sea. There are lots of problems with using plastic. It is actually not a stable material, and while it'll last forever, it really isn't a structural material. that can handle the movement. And in this sea, we have here about 8 million waves a year. So you've got, a pretty high movement on something. So then I built it out of steel, 2016, and made electricity with this. But the problem was this is a floating device. The reason it's floating was so that it would move up and down with the tide. We have the 16-foot tide. So that didn't work very well. So then I thought, well, I can put a heavy weight on it, which you can see there. There's, I think it was 30,000 pounds. And I made bigger tanks to have more buoyancy, and then put a huge bunch of weight on them. And that worked very well for waves that were less than half a meter. Over half a meter, everything moved with it. So unfortunately, that didn't work. Then I thought, well, Wavestar does it with that float lever arm. And with the lever arm, I can get some mechanical advantages. So I tested that, found out how it would work, and then built a system. This is when we first went out of UBC. Put that in, and basically it broke. And so we abandoned that and went to donut on a stick last year or 2 years and put that in. And now I've gone all the way back to putting the pile in, putting the float on the pile, and letting the float moving up and down the pile. And so we were testing that, and then I put the test station in this year. Next year, it says 2021 NEP 7. I'm modifying the float right now. I'm modifying the PTO, and I'll open the testing station in the spring or summer of next year. So now I'm coming to the section I call the formula section. The first thing is that we have this thing called HS, and it is absolutely not suitable for somebody that's doing something practical like trying to predict or work with the waves. It is an artificial number from my point of view. It's a statistic. And the purpose for HS is safety. You use it to build things so that you know what the maximum force is that's going to come. And captains, and we all remember just a while ago in Ucluelet or Tofino, a boat flipped over because the rogue wave hit it. Well, the HS tells you how big the rogue wave will be, and you better be on the lookout for it. And otherwise, people will die, as we have seen. So it's not about, it's wrong to use this number for energy, and you'll see that in a second. And that's my point. And what's really needed, and that I've been trying to work on, is, maybe you guys can do, is give me a factor that I can multiply the HS number, which will give me a reasonable average wave height for the period of time that it's there. It's usually an hour, but sometimes it's half an hour. And the best number I've got is from NOAA, and it's 0.64. It's really quite small compared to, you can see the numbers there. A 1 meter HS is actually just a little over a meter average wave height. I don't know if there's more to say about this. It's a very important thing. It's all clearly laid out right there. Now, from my point of view, I did applied science and got into some vectors with structures. I've had a lot of trouble trying to understand wave energy, wave power, and what's going on. I made this to help myself understand this, and I completely spend my time thinking about wave force. And I just stay there. I imagine that it's this dimensionless entity that has no weight and is just simply a live, active force. And that's what I'm trying to deal with. When I start trying to design working with the energy or the power, I find that I'm unable to work with those, with the force in that world. And but the entire wave energy world works with energy and power. And here are the three formulas. Each one of these has lots of variations, but they just vary at just enough to make it slightly different. And the first one gives you joules per square meter. And of course it uses the significant wave height, HM0, and the papers show that HM0 is about 5% bigger than HS as reported by the weather people. The other thing I should say why HS is so important is that you can find the HS for any part of the ocean in the world. It's really a readily available value. And so there's no question we have to work with HS, but we have to know that HS is really, it's almost twice as big as the real thing is. And people make calculations using HS. They build machines which cost $20 million, and they find out that they don't get the same amount of power that they thought they might. That's what I really think is going on. And there's this epidemic of not showing the power that's been produced by all those machines that governments have spent so much money on. And I think it's partly because they're working with these formula. What I've done in this first slide on the left is taken those three formulas, used them with the Halibut Bank hourly data, and there's the difference in the formulas. I've used the first one, which gives joules per square meter, divided it by the period, and got myself watts, and then in this case, with respect to the what's going on there, the bottom line is the wave height, and what I'm showing there is the wave height that I call the actual wave height from 0.1 of a meter to 1.67. The HS number would be around 0.3 or 4 and goes up to a little over 2. So those are those. This is what I'm getting in my test on this right-hand side, and the blue line is the one from the formula, which you can see on the other side is hardly gets up, doesn't even get to 20 kilowatts, but when you zoom in on it, and I don't make the screen so big, that's what we've got. That's what I'm getting. Now, when you talk about the kilowatt hours, so then you have to add in how many hours there are for each wave height and each wave period. That's where you get that scatter chart from. And when you use that scatter chart and you use those formulas, that chart shows, that's what I get when I do it. Formula 1, Formula 2, Formula 3, and what my test data is. This would be kilowatt hours. And we're using the Halibut Bank data. And here's another chart of that, which shows it in a different way. And yeah, so that's basically the end of the formula section. And now the future is that what I've been able to get is continuous variable electricity. I've been approached by people to use it for hydrogen electrolysis. It's a very energy consumptive activity. However, in a way, it's like a battery. You can use the wave energy, which is variable, or solar energy or wind when it's available or not needed by the grid, and then direct that into the hydrogen electrolysis process. And then you can store that energy as hydrogen and then move it around and use it. I've also learned that Vancouver and the BC government's projections for what do you call it, green power by 2030 is going to put a burden on BC Hydro. And I believe I've heard them say they don't have enough power in 2030 if all of our transportation is electric. And they are actively promoting hydrogen, particularly for transport trucks, buses, heavy duty transportation. Probably the cars will be electric, but there's going to be a problem and we need to do something about it. The next thing is that the wave energy can work as a direct drive system for desalination, because really desalination is a pump. And so instead of converting the wave energy to electricity and then using the electricity to drive a pump, you can simply use the up and down motion of the waves to build up the pressure to force the salt water through the membrane. What you've got in front of you is the result of a report I gave to a company in Belgium. And what they were saying is our wind turbines are there, the infrastructure is in, but they're not producing as much power as we would like. And is there some way we can add something to them that would utilize the waves, and then we could use the existing wind turbine infrastructure? This was the proposal I came up. And so what we've got out there off UBC is a single small piston float. And in this drawing, I've got 24, and I think that I'm looking now to build them up to 32. So I'm just looking for a project to do this with, or something that's similar to this. There is some discussion about the fact that when the waves come to the first float, let's just say it was going past this from the direction we're looking at it, that the back floats would then not have as much wave energy available to them because it would be taken out by the first floats. And I disagree with that. I've made tank tests and measured it very carefully. And I think why I'm getting higher numbers than the formulas show, and that's the main reason why I'm building the test station, so we can go there and actually, I can prove that to you, is because there's something going on here that isn't actually articulated in those formulas. So there you go, I'm finished. Thank you.